Good evening and welcome to this CIBSE HVAC Specialist Group event. While we're waiting for just a few more people to join us, I will do the usual housekeeping. So this event is being recorded and you will receive a CPD certificate for your time. We obviously do hope to keep delivering you subjects that are relevant to you. So if you have any ideas about future events, we would obviously love to hear from you. Please do contact us via the emails that you see on the screen there. Alternatively, we would ask if you could post any ideas on the Q&A chat today, and we can take them away and hopefully come back to you with an event. So if you would like to become a member of our group, please log into CIBSE under my profile and you can see there under groups and network, you pick the groups that you want to be associated with. Obviously, as the arrow's pointing there, HVAC Systems Group. So on to the main event. And today we will be discussing indoor air quality. This is obviously a topic that must be viewed with even more importance in the post-pandemic design. This session will comprise of an hour of presentations from our guest speakers, followed by a half an hour of Q&A. And please do feel to post your questions along the way in the Q&A section, and we will aim to respond to these later on in the evening, in the event in the evening. So my first speaker is Professor Pawel Wargocki from the Technical University of Denmark. So Professor Pawel graduated from Warsaw University of Technology in 1990. He received his PhD from the Technical University of Denmark in 1998, where he has been teaching and performing research ever since. He has over 25 years of experience in research on human requirements in indoor environments, and he's best known for his seminal work demonstrating that poor indoor air quality does actually affect office work and learning performance. He is the go-to for indoor air quality in Europe, and we can hear from him now. I just wanted to add, just before I pass over to you, Pawel, that he does have to leave us a little bit later in the session. So if you've got any questions, put them in the post. If we don't get back to you, we will look to respond to them as we go a bit later on. So over to you, Pawel. Thank you.
I want to share this. Oh yeah, now I can do it. Sorry. Okay, we have tested it, and of course, then I realized there is some new information on my screen. Thanks a lot for the invitation. And apologies at the moment for two things in the beginning. As the first one is, I'll not speak a lot about COVID-19. That's one thing. The other thing is that I cannot stay until the very end for the question and answer session, but I would be very happy to answer any questions if you just post it to me via email. So today I'll be speaking on how we could develop the indices for defining indoor air quality. We have very short time and the topic is rather big to discuss. However, I'll try to put it together and explain to you. I will not speak about COVID-19, although the recent science paper by Morawska, I am one of the co-authors of the paper, actually argues that the viruses or pathogens, that the airborne pathogens, they should be included in the guidelines for indoor air quality. However, at the moment, we don't know how to monitor them and how to measure them. So I'll focus on these aspects that we can measure and we used to measure in the past. I think I will start by saying something that is quite obvious to us, all of us, is that, and it's actually citation from the paper that we published together in 2016, is that there is necessity for indoor air quality metric. And why there is this necessity? It's, first of all, it puts us in a different situation compared to any other disciplines or any other areas that have metric. And so basically, it's very difficult for us to argue and discuss if we don't have a metric that we can use in different buildings and benchmark different buildings and so on. Furthermore, without IAQ metric, it's very difficult to innovate and advance our field and our science. So it's very difficult to improve indoor air quality if we don't have a metric. Actually, we have some metrics, and we used to have some metrics, and we used to have some proposals for the metrics, and I will try to review them in my presentation. So objective of my presentation is to review some indices that and approaches used so far to characterize and define indoor air quality, and I will actually discuss a little bit about their limitations. And then I will review recently developed or planned rating systems, and then discuss the potential strategies for how we can set an index of indoor air quality in the future. And it's obvious that we need such in the future. And we need to make an agreement there, and how we can do it, it's just the decision to be made. So before we develop the indoor air quality, we need a metric. We need to understand how indoor air quality is defined. And basically, it is defined, there are several different definitions of indoor air quality. And basically, it is defined as the air quality within and around buildings and structures that relates to human health, comfort, human health and comfort. And basically defines different types of pollutants, chemical, biological, and physical contamination, and sometimes, and defines also harmful concentrations that cause the discomfort or reduce the perceived air quality or the perception of the air quality. And also some of them talk also about the temperature and relative humidity as the aspects of the indoor air quality. So there are different definitions, but generally they come up to one common denominator. It is saying that if we talk about air quality, we should talk about pollutants that are indoor and outdoor, because the outdoor pollutants enter inside the buildings, and they should include gaseous pollutants, particulate matter, and biological agent. And this is the only connection here to viruses, COVID-19, or basically the airborne pathogens, because there are other pathogens as well that can be in the area of the buildings. However, until now, we don't have indices that particularly address one of those or all of those pollutants. We have some sort of a markers or indices of indoor air quality, which are indirectly related to the levels of pollutants. And also, we used to have markers of indoor air quality that either looked only on the volatile part of it, or maybe looked at the human response, perception of air quality, or maybe human generally rating of the air quality. So the most popular are the ones that I used is ventilation rate and carbon dioxide. And let's start with the ventilation rate. Well, ventilation rate, in a sense, is sort of a solution that, because we cannot identify the pollutants of concern, so we use ventilation because it can handle most of the pollutants. And that's the common belief, is that ventilation can be used to basically remove any type of pollutants. And whether this is the case, probably not always. Also, we use ventilation, and we believe that more ventilation always improves indoor air quality. The lack of ventilation or low ventilation rates means poor air quality, and ventilation can be used, can be a performance-based metric, basically can be used to predict human responses. And however, if we think about how ventilation is modifying human responses, such as health and comfort, so ventilation is not the indirect relation between the human responses or outcomes. It is actually a modifying factor of exposures. So indoor air quality should be basically developed based on the exposure levels and human uptake of some of those pollutants that affect the human responses. And ventilation can only modify these exposures, some of them, maybe not all. And there are also other means on how those exposures can be modified. So ventilation is an intermediate index of the level of air quality. It's not a causative factor of what we are aiming at is to reduce negative or adverse effects of indoor exposures that affect health and comfort of occupants. So at the moment, we use ventilation, but it is simple, relatively easy to verify and readily available, but it's used to, as used today may not be considered as a solid and credible metric for predicting indoor air quality. I don't have more time to speak about aspects such as ventilation may not affect all the pollutants, all the exposures. Not all the exposures will be affected by ventilation to the same level and the same in the same way. And also, the other aspect of ventilation is that it is not a direct related to human outcomes. So, so this is a very important point here to address. Then, for years, CO2 has been used, and of course, CO2 has been used throughout the history very often and referred to. And it started with the 17th century discovery that the presence of CO2, which was called at that time ineo aerial particles produced by candles, caused the demise of animals, and that was Lavoisier who actually attributed this effect to CO2. And the CO2, rather than lack of oxygen, was considered to cause physiological effects. And then Pettenkofer proposed CO2 as a marker of indoor air quality, and we know that famous level of 1000 ppm that is differing, you know, from the air that is polluted or poorer quality above 1000, and the air that is less polluted, which is below 1000. Also, CO2 has been used in the classical studies that were done in the early 20th century in United States that looked at the ventilation requirements in buildings, which are attributed to the pollutants emitted from humans. And back in the last maybe 5-10 years, CO2 has been also discussed in the context of the direct effects on humans. So if we use a CO2 as an IAQ metric, actually CO2 is a metric of the ventilation, because actually it will provide us with the information about how much outdoor air is coming indoors in the spaces that are occupied by people. So basically, it should be put together in the same group as the ventilation. That's the index of IAQ, and is actually only used and can be used when there are people in space. However, CO2 it's maybe easy to measure because we have monitors available, but there are certain time effects of this. Is highly variable. Often steady state are assumed, but very nearly never reached. And then it requires assumptions regarding generation rates. So if you want to convert CO2 into ventilation, for example, or how much air is provided indoors, we need to know how much CO2 is emitted by people. So, so that you need to assume, and those assumptions may be incorrect, basically. So, because it is a marker of ventilation, it contains all the same pros and cons as ventilation, as I mentioned earlier. Then TVOC was used, and the TVOC is a total volatile organic compounds. It's the addition of masses of polluting molecules, and basically it was defined as the masses between carbon-6 and carbon-16. And that was a very popular metric in the 80s and 90s, and then it's coming back now because of the prevalence of sensors on the market measuring so-called air quality, basically by using the same concept, measuring the whole spectrum of pollutants and expressing it in one number. So for that purpose of defining air quality, and mind that this is only volatile organic compounds of between this carbon levels, C6 and C16. So all the other compounds, such as semi-volatile organic compounds and very volatile organic compounds, are not included in that metric. Also in that metric, there are no other pollutants included, right? The particulate matter is not included. Then there is also the viruses and biological is not included, biological pollutants. So then for that metric, there was those response relations were developed by Mulhave and by Seifert that related TVOC with the certain human outcomes. And basically they come up to the same level of 200 micrograms per cubic meter of TVOC. And then defining also the levels for the specific types and groups of pollutants, 200, 300 micrograms per cubic meter. However, because different definitions of TVOC were used, the literature was not able to basically find the relation between that metric and the human outcomes, or systematic relation. Therefore, TVOC has been basically rejected or not used longer, because it was very difficult to find that relation with human outcome. And then we have assessment by humans. So basically we can ask people to evaluate the quality of air quality by the extent to which human requirements are met. So it is in the standards. European standard EN 16798, ASHRAE standard 62, is the prescriptive numbers are based on this type of evaluations. And basically they define the level of dissatisfaction that is caused by air quality by people assessing the air entering the space. However, there are several factors that disturb precision of those ratings. And again, this is not a very solid metric in a sense, because it will be depending on the type of measuring scale, group size, different methods on how you transfer the responses to some dissatisfaction level. Temperature and relative humidity is a very important parameter that will interfere with those measurements. And there are also some adverse pollutants that do not cause sensory response and are not addressed in this. So basically, there have been those attempts made, and then they only addressed or mainly addressed exposures to chemical compounds, neglecting other pollutants. And they usually address one modality, it is comfort or perceived air quality. And they mostly are related to ventilation compliance. So were there any other metrics? And of course, I focus on those major, but there have been several other metrics that are listed here, and you can study them afterwards very carefully. And I can also provide you the reference to the paper which summarize those. So they were proposed, tested on 1 or 2 experiments, and they never surfaced. In a sense, they have never been used afterwards. So there have been several attempts of that. Recently, I would like to mention 2 attempts that have been made. There's one attempt that was proposed by the Annex 68, which is the International Energy Agency annex, supported by International Energy Agency, that developed the metric based on the pollutants that are measured in the low energy residential buildings. So the idea was that from an energy modeling aspect, we need to know how does energy changes or changes to the building energy performance affect the air quality. So there was a need to develop some sort of a metric or some sort of a group of pollutants that can be used in models to find out what is the subsequent effect of the result of the simulation. So 16 target pollutants were developed. So the idea for the metric was to select the pollutants that were typically measured in low energy residential buildings. And these are the 16 pollutants that were proposed. See, carbon dioxide is there and TVOC is there, and these are not the pollutants actually, but these are markers. And then the idea was to compare them with the long-term exposure limits and short-term exposure limits existing, and basically create a metric that is based on the comparing the measured level of pollutants in buildings against their short-term exposure levels, long-term exposure levels for the acute effects, and calculate the disability adjusted life years, DALYs, for the long-term effects. and for those types of pollutants. So that, again, you can see there is a PM there, and then there are volatile organic compounds. Again, that has been proposed. No further developments have been made. Recently, another metric was developed, which is called TAIL. It is a rating scheme that was developed for evaluating the overall quality of indoor environment. So you have an element of thermal environment, which is T, acoustic environment, which is A, indoor air quality, which is I, and luminous environment, which is L. And I will only focus on the indoor air quality part because this is the topic that we are speaking about. But generally, this rating scheme, the idea is basically to evaluate all those parameters that define indoor environmental quality, or components of indoor environmental quality, and then define overall indoor environmental quality, which is by the Roman number in the middle of that. So the colors here define the levels of the quality of those components, and then inside it's the overall indoor environmental quality. But if we go back to the indoor air quality part of that, so for that you can see there is no any metric. So for example, for thermal environment, acoustic environment, and light, a simple measurement was proposed to determine the quality level. For indoor air quality, there is no metric. So several different pollutants were selected, and these were basically the ones that are normally used, the CO2 ventilation rate, and those that are in the WHO air quality guidelines. What could be other methods of defining indoor air quality metric? Well, we have the QALY and DALY. QALY is used in the UK, so you should be able to know it's a quality adjusted life years, and DALY is disability adjusted life years. And these concepts now are actually, how to say, investigated or examined in another annex that was recently supported by International Energy Agency. It's Annex 86, and subtask leader that is responsible for this metrics is actually Professor Benjamin Jones from University of Nottingham. So there is an attempt in this particular subtask to develop the metric for indoor air quality based on the QALY and DALY approach. To finish up and summarize, so I provide you with, I do not have a solution for that, and I don't have any answer how the future indoor air quality index should look like. I think what we really need to know is basically we need to focus on 3 steps. So we need to first, which I call it why, what, how. It is why we want the metric, for what purpose we want to have a metric, and how we want to define the markers on indices. So why we want the metric, you know, now we have on the market several different types of sensors that are used, and they provide some information to their users. So that could be one reason why we want to have a metric. But there could be any other reasons why we need to have a metric. It's a stamp of indoor air quality conditions, or input for the control of building systems. So this is all depends why we want to have a metric and what for which purpose. The second step is what, and what is very important because we need to define the compliance criteria. At the moment, we only focus on comfort with DALYs and QALYs with the focus on health. But what about productivity or the cognitive performance, effective time at work, and learning at schools for children? What about the sensitive individuals? So that is something also to define what should be the compliance criteria for the metric, and then how we should define these metrics. So should we define it as a single compound, or a group of contaminants or pollutants in the space, or something else? So this is it. This is my contribution to initiate the discussion on that, and a short look at what we know about the metric and how different indoor air quality metrics were developed in the past. Thank you very much for your attention.
Pawel, thank you so much. That's fantastic. Really interesting view on indoor air quality. We do actually have one question that's come in. Have you got time for that one?
Yeah, of course.
From Ron, and he's asked, stable and accurate calibration of VOC sensors is hard and expensive. Do you see sensors that output based on the direction of travel of the ppm as suitable?
It's very difficult to answer that question. I do not see that. You know, even for CO2, we see the problems because of the self-calibrating procedures and so on, so on. So at the moment, I think what we really need to understand is where we should focus, on which pollutants we should focus. I think what the sensors that are available on the market is the sensors that are providing some signal. The important question would be whether the signal is relevant for human outcomes, or is it providing any information that can be related to our comfort, health, maybe cognitive performance. So that probably for PM sensors, it is much more, it will be probably easier to develop because that is a focus on one type of pollutant, which are PM.
Lovely, thank you. And there is just one more that's come in.
Sure.
Yeah, so always good to see a multifactorial approach in the indoor environment. Do you find that the level of personal control over the environment is a confounded variable in comparing the multifactorial physical matrix with qualitative response?
Certainly, it's certainly, but you know, it's a very difficult topic to address because, you know, for the facility managers and designers, we really don't know who is coming into the building. So we need to know some level of the average response for the people. But of course, when we have and that probably the metric, that should be one metric, or maybe the metric, is developing a sort of a base conditions. And then it's very difficult at the design stage to predict all the individual responses. So that should be addressed with the sophisticated or advanced solutions to address those aspects of people. In the studies, if the question is about the studies, of course, that is addressed by having a large group of people responding and averaging across the entire population. So for the small groups, yes, that would be a very strong confounding factor. For the large groups, that probably will be averaging out, and we will see the average response with a standard deviation, sort of a base condition.
Great. Thank you so much for your time.
Thank you very much. Thank you for the invitation, and apologies that I cannot stay until the very end.
No, that's fantastic. Thank you.
Have an enjoyable and great the remaining part of the meeting.
Thank you.
Thanks a lot.
So moving on, my second speaker is Peter Dyment, the Technical Manager at Camfil Limited. Peter has been working in the air movement and air cleaning industry for over 40 years. He has participated in international standards development for air filtration performance and energy efficiency to deliver clean, healthy indoor air. Cost-efficient, clean air solutions to meet current needs are his key motivation. I will now pass over to Peter.
Thank you very much. I hope you can hear me, Rianne.
Yep, thank you.
See if I can get my slides up. Maybe you can confirm they're on view.
Yep, that's fantastic. Yep, all there.
Good. Well, thanks very much for the opportunity. As has been mentioned, I am an air filtration engineer, so I try and keep things as simple as possible in providing solutions that are effective for current needs. And tackling indoor air pollution sounds like something I could very much address as an issue. And that involves ventilation systems and bringing outside air into the building, which quite often is not as clean as it should be. So when people talk about fresh air, in actual fact, when they're talking about outside air, it will more than often than not contain particulates and gases, emissions from traffic, and other combustion going on. As you can see here, smoky Westminster, that sort of outside air in the city UK environment we're all aware of. So that's something to be aware of if we're drawing in ventilation air. And then, of course, apart from the outdoor sourced pollutants, we always have the indoor ones as well. And over the last year or two, it's become apparent that breathing air indoors can actually kill you if you happen to be inhaling a certain virus, which we all very much know about. So air pollution is dangerous and hazardous to health. And of course, COVID-19, these are particles, but you also have the gases, and indoors you've got, as Pawel mentioned, you've got VOCs and you've got aldehydes, formaldehyde, those sorts of things, which also can have the capability of making us very ill. So looking at the COVID-19, it is, as I say, a particle problem, small particles, 0.12 to 0.16 microns. Microns a thousandth of a millimetre, very small. And when you get infected people in the indoor space, they cough and sneeze, even breathe, speaking. They can project out droplet aerosol particles, as they're known, and these can cause problems. For quite a while, it was thought that a lot of it was done by contact and that sort of thing, but it's become quite apparent over the last year that the issue has been very much also tied into airborne aerosol clouds, and so government guidance, as you can see, has been evolving over time. It did talk about opening windows initially with very little detail, and then they've become very much more focused on particles being the issue, and indeed wearing a face mask has been broadcast as a good thing, which has to be from my point of view, applauded, because they are in fact, essentially an air filter for your face. So, and they do benefit to the people who wear them, but also to the people who are in the area, particularly if you happen to be infected. So, removing particles is something from the air which air filtration is particularly good at. And we're in a time of change. The WHO, World Health Organization, have just recently increased their scrutiny and guidance by reducing exposure levels for, in particular, particles, but also nitrogen dioxide, which is a particularly nasty part of traffic emissions. And you may well know the Deborah landmark case recently, where Professor Stephen Holgate convinced the coroner that the reason for the death of Ella was the continual exposure to nitrogen dioxide over a long period of time. And so that has to be rated. And in fact, the WHO reduced the long-term level, as you can see there, from 40 micrograms per meter cubed as an annual mean down to 10, which is a fourfold decrease. So they take this very seriously. And of course, fine particles, the other thing that's extremely hazardous, they've reduced that from 10 micrograms to 5. And just to clear a point, the guidelines are applicable from the WHO for both outdoor and indoor environments globally. They cover all the settings where people spend time. That's on about page 20 of the preamble of the 300-page report. So absolutely clear cut there. Changes have taken place. It's taken 16 years for these to be revised, and they've been deliberated over by hundreds of the world's top medical experts and supported by about 250 study papers. So this isn't something that's lightly been taken on, and it should be taken into account with assessments for what is regarded as clean air or otherwise. There are also supporting technical standards. I think Pawel again mentioned briefly EN 16798. Part 3 is the bit I focus on because it regards categorization of air and uses SUP and ODA and RCA, different types of definitions for air, inside, outside, recirculation. And you also have very good test standards for covering particle air filtration and gas filtration, the two types of pollutants you're likely to come across. And those are underwritten by Eurovent, the European Manufacturers Association guidance for the requirements for clean air, an application of air filtration. So it's a very good document, recently updated in November 2020. And the WHO guidelines I've just talked about, they were updated literally a few months ago. So this convergence of standards and guidelines means we really do have a good framework to work in if we're coming up with effective solutions to clean indoor air. And let's get it absolutely clear. It is clean air that is healthy air. And so air monitoring indeed has become another requirement now, given the better technology that's available. This just gives you a quick idea of the SUP is supply air coming through the ventilation system into the building, hopefully having been filtered. ODA is the outdoor air. So the difference between the two, if you like, is the difference a good air filter can make in terms of cleaning the air. So if we want a good ODA2, which is your sort of general purpose office type environment, and you want it, a good SUP2, should I say, indoor office environment, SUP2, and you've got an outdoor city environment, which would typically be ODA3. So you'd come across from ODA3 on the horizontal axis there and cut across the SUP2 in order to have the required filtration to come from that level, the dirty level of outside air down to the clean level of inside air required. You need an 80% efficient filter, and that would be an EPM1. In other words, an 80% efficient filter at removing PM1 particles. That's particles 1 micron and below. So that just gives you a quick flavour of the classifications there. You can have even cleaner air for SUP1, which would be a 90% EPM1 filter from ODA3. And you can have lower grades, which don't really reflect constantly occupied buildings. In other words, places like car parks or storage areas, that sort of thing. So that just gives you a quick flavour of the frameworks we're working on and the monitored air pollutants you're likely to come across. So what do we want in terms of an overall strategy then, in terms of dealing with outside air and recirculated air and air that's being passed around inside buildings? Well, ASHRAE came up with a very good core guidance document for reducing airborne infectious aerosols, again aimed at COVID-19. It gave certain requirements here which you can follow through. It's all very good actually, apart from the MERV ratings, which unfortunately ASHRAE 52-2 is not quite up to date with ISO 16890, which is a current world standard, which should be used as its methodology is very much up to date with the latest accurate measuring methods. So if we have a utilisation and upgrading of existing ventilation systems, improving ventilation filtration, both for supply air coming in from outside, but also recirculation, whether that's the main air system itself or standalone air cleaners or air purifiers. We can monitor the air and demonstrate effective delivery of clean air into the building. Air cleaners standalone tend to use HEPA filters, and general HVAC systems use the ISO 16890 with a high EPM1 reduction for their classifications. And I would stress that air filters need to be constantly monitored for their effectiveness. Are they well sealed into the units, well engineered? Are they delivering clean air? Maintained so that they're not left to become over dirty, consuming heavy amounts of energy. They need changing, monitoring, changing when required. The data of the air, how clean it is, what the pressure drops are across the filter to make sure they're due or not due for change should be constantly monitored. And then again, adjustments should be made should you find any problems based on the data. So this is something that can readily be done by maintenance engineers and people who are interested in these things. And indeed, air monitoring now is becoming a very common thing to have inside buildings. So these are all step-by-step steps that can be taken to improve the situation. I'd just like to quickly move on to this study from Addenbrooke's Hospital. When I saw it, my eyes lit up when I saw some of the findings. This is an NHS hospital, Addenbrooke's Hospital. Cambridge University's did this study. Dr. Andrew Conway Morris, who I've been in contact with Cambridge University, did some real world monitoring. How they did it, I just don't know, in the beds in a COVID ward back in January, February time, when we were all very much under the cosh. We were all spending time indoors. They went out and they did real life monitoring of COVID wards, levels of the COVID aerosol in the indoor space. As you can see, these people well protected, fully loaded beds. They were 100% occupancy. They actually tested the size of the particles in the air. They did air sampling over a 3-week period during the peak of this upsurge event. They measured particle sizes below 1 micron, 1 to 4 microns and above 4 microns on their air sampling device. And the thing that sprang out to me as an air filtration engineer was, over the whole time of this period, whether they used filters or not, they were not able in the background to determine any infectious SARS-CoV-19 RNA in any of the particles below 1 micron, which I find an absolutely key piece of information. I'll probably keep repeating it till hopefully people will realise the significance of this. One of the statements they made in their paper was that cleaner air will reduce the risk of airborne disease transmission. So this is a very important step forward. And as I say, they, over the 3-week period, they monitored the air, whether the filters were on or whether they were off, and they used a NIOSH aerosol sampler every 6 hours to check the data for these various particle sizes, and at no time in the small particles, whether the filtration was on or off, did they detect any particles below 1 micron that carried any virus RNA. In other words, there would be nothing there that could possibly infect people in those small particles. So therefore, you don't necessarily need air filters that will go down to particles that are sub 1 micron to any great extent in order to protect people. So that tells you that the proposition would be, if there are no RNA in these very small particle size range, then ISO 16890, which are PM1 to a very high efficiency, are capable of removing infectious particles in the 1 to 4 micron range and above 4 micron. And this should be something that is more closely examined as being a potential greater level of protection to people, not just in hospitals, but also in general offices. We have hundreds of thousands of air handling unit systems around the country where you could upgrade filtration and even re-engineer to have recirculation to protect people, both against air pollution from outside, traffic air pollution, but also recirculation, reducing levels of infectious aerosol. You can just see here some of the results when the air filters were off. COVID aerosols being measured in the larger particle size, filtration on, and they disappeared, filtration off again, they registered again. A clear benefit for standalone air cleaners, but also they monitored for general levels of bioaerosols, not just COVID-19, but all these other, but obviously airborne particles that were gathered by the samplers, which again would let me lead to the indication that maybe air filtration should be more generally used in the indoor space of hospitals if you are having this situation where you have a large virus bacterial particle load in the atmosphere, which can be drastically reduced. They did in this virtually get rid of the whole lot when the filters were on. There was just a very small sample of fungal spores picked up on one of the days. So that shows how effective air filtration can be when it's properly applied. And they did in their report say, we consider these data suggest that these precautions may be more important in conventional wards as well as well-defined or even more so than well-defined aerosol risk areas. So air filtration can be selected for very high efficiencies, and it can also be multi-staged. So you can see here a selection of filters, and indeed they show very high efficiencies in the small particle size range. This is below 1 micron going down to 0.3. You can see here as you go up the range here, the particle removal efficiencies here are very high in these particular filters here. These two are landmark filters because they can be used as single stage filters as well as multi-stage, which is a very good idea because then you can actually minimize the energy consumption. You don't need pre-filters with these filters. They can be used, or they can in fact be used as pre-filters. So if you look at this, you can see here a multi-stage filter system. There are, as I say, hundreds and thousands of these legacy systems that might have air boxes for mixing air, recirculation air. They may not have heat recovery systems built in. They may not have heat wheels. They may not have run-around coils, but they do have a damper system where they could recirculate the air. And if they do have that, rather than having the knee-jerk reaction of turning off recirculation, if you filter the air coming back through with a 70% EPM1 rated filter and have it introduced upstream of the supply air side filters coming back into the building, that would be 3 stages of air filtration, as you can see here, before the air makes the circle through those and comes back into the indoor space. And you would, of course, be able to reduce over 3 stages for PM1 97.3% for those 3 stages of filtration as a cumulative efficiency. In fact, if you were looking at PM 2.5, that would be a 99.2% efficient. So that would be up in HEPA efficiency for those smaller particles there in that sort of range. Very high efficiencies. So if you take into account also that the air change rate, 5 air changes, that means every 12 minutes you're rechanging and changing that air in the indoor space. And if you boost it to 10 air changes per hour, that would be every 6 minutes. So if you introduce a proportion of that air back into here, it used to be 80% recirculation, 20% outdoor air to keep the oxygenated levels and remove and dilute carbon dioxide. You would actually possibly save huge amounts of energy in terms of having to heat air, because if you have 100% fresh air, which is what, or outside air, I would say fresh air, outside air coming into the building, you have to heat that, and it's an incredibly high heating load, incredibly high energy use. We need to be finding ways of reducing that energy consumption. Remembering COP26, it's very important. We need to be looking at ways of minimizing energy use for heating and cooling, and that could be if you only have to have low outside air topping up, 80% of that heat might be saved and recirculated as an ongoing process. So this is something that needs to be investigated and applied much more rigorously than previously. We already have widespread use of the recirculation of air in freestanding air purifiers and air cleaners, as has been demonstrated with that Addenbrooke study we were just looking at there. These are extremely effective in terms of removal of viral particles. But instead of looking at the actual viral particle itself, which is around about 0.12, 0.16 microns here, if we're finding out from that study in actual fact you've got to go above 1 micron here, then you've got incredibly high removal efficiencies here up to this range. So and indeed ISO 16890 filters are extremely efficient in this particle size range. So I think we're just really neglecting a really good weapon in our arsenal for keeping air clean and healthy for people to breathe without risk to health by investigating the potential we have here. So most penetrating particle size, that would be, for example, for an H14 commonly found in air purifiers, 99.995% removal efficiency at 0.13 to 0.16, which is the virus particle size for COVID-19. So that's an extremely effective solution. So standalone air purifiers will deliver in an extremely short period of time. This is a particle count showing the reduction over a 25-minute period. So 0.3 microns, that goes from sort of 30 million particles per cubic meter down to a couple of 100,000 over that period of time. If you just leave that to work in an indoor space, this was about 40 cubic meters, an indoor office space over about a 20-minute period. So extremely effective and extremely useful. And just to show that small particles are the ones that get into your lungs, this is a quick demonstration here. If you look at that sort of penetration level, 84% of particles in the 0.15 to 0.5 range, which is where typical COVID-19 aerosols and fine combustion particles from traffic usually are in the size distribution range. You can see you need protection of that by having PM1 high efficiency filters, and you can see once you get above the 1, the body itself has much better removal efficiencies in the nose and sinuses, but you still do get some penetration into the deep lung there. So EPM1 rated filters are very necessary for removal protection. Here you can see energy efficiency ratings for filters. These are now published widely on the Eurovent website. A+ rating for a filter means it's extremely energy efficient, so you get a good combination of filtration efficiency for removing the particles, but also minimum energy consumption based on low operating pressure drop. This particular filter here has a 60% PM1 efficiency, whereas some of the low efficiency panel filters on the market have the same energy consumption, but they're only 3% efficient for removing fine particles. This one here this filter can be used as a single stage filter, so it's extremely good. You can see the traffic lights here, A+ to E, very efficient down to not very efficient. And this is a good way of having a quick visual aid and seeing how efficient people can get their filters. And this is worked out by this equation here as an energy model based on air passing through a filter and the increase in pressure drop over time. So I'll leave this with you because we do have limited time today, but I just wanted to point out you could do a very similar thing for IAQ based on the World Health Organization levels that has just recently been published here. This SAGE independent report 51 here was advocating use of a traffic light visual display here. So I thought to myself, well, if you take the WHO levels they've given here, the annual means, which we would normally use for calculating filters and cleanliness of indoor air, you put those here as a reference. You use the WHO limit here for PMs, 5 micrograms per meter cubed. You have a factor down here or up here, excellent, very good, which is half the level. The actual level itself, 2 times, 4 times or greater, which is considered to be not very good. For PMs, 20 or above micrograms per meter cubed. For NO2, 40 or above, not very good. And you can write your own monitored levels in here very quickly and get a feel for whether your indoor air is good, bad, or indeed even outdoor air. So this is a very good way of looking at something which could be very useful to people and very informative if you're not an expert. So take the WHO, the world's experts, take a nice visual guide, put them together and bingo. It's an idea to talk about. So looking at the possible levels we have, you've got lots of solutions. I think we're pretty much running out of time here, so I'll take that as a cue to finish, but we have nitrogen dioxide filtration and we have standalone solutions as well. You will see the slides, and if you have any further questions, do come back to me.
Absolutely fascinating, Peter. Really, really interesting presentation. I am aware that we are getting a bit short on time now, so I'll ask you, Peter, if you could respond to some of the questions in the link while I now move on to our next speaker. So David Black is the Global Product Marketing Manager for Modular Air Handling Units for Flat Group. He has worked in the HVAC sector since 1986. For English, German, Swedish air handling unit manufacturers. He is actually one of our CIBSE HVAC Group committee members and sits on referent groups for Eurovent and contributed to materials of the CIBSE COVID-19 ventilation guidance. Over to you, David.
Thank you, Marianne, and thank you, Peter. Hopefully you can see my slides.
Yep, that's great.
And hopefully they've woken up. Because my slides sometimes take a while to wake up, a bit like me in the morning.
You're fine.
The subject of my presentation is air leakages and air handling units guidelines and indeed guidance for improving the indoor air quality. And it follows on pretty much from what Peter's been saying. It's all very well to have very efficient filters in your air handling units, but if the air handling unit itself leaks, then we've almost certainly got a bit of a problem with the indoor air quality. And it hasn't yet woken up. There we go. So where do air handling units leak? They leak around the filters. So we might put Peter's filters in the air handling unit, but if we get leakage around the filters, the filter by its very nature is less effective. We can leak in or out of the casing, and we can leak in or around or through the heat recovery system or heat recovery device or heat recovery component, whichever way you want to describe it. So is that leakage important? There is reference to it in EN 16798-4, common features of heat recovery systems. It says that the leakage from plates or heat pipes or rotaries, leakage from plates and heat pipes is slight. From rotaries can be considerable. Runaround coils, obviously, with separated airstream, there is no leakage. But what is the leakage possible in the case of a defect in the heat recovery device? It could be large in the respect of plates, heat pipes, and rotary heat exchangers. Of course, runaround coils, separate airstreams. So what effect could that have on the overall system and what we're trying to achieve with an air handling unit? The supply and extract volume flow could actually be wrong if there's excess leakage in the air handling unit. The SFPV could be wrong. The heat recovery efficiency could also be wrong. And most importantly for the subject of tonight, the indoor air quality might be poor as a result of leakages in the air handling unit. And that, of course, could contribute to some COVID material being recirculated by the air handling unit back into the occupied space. There is a document, it's published by Eurovent, and it's the best summary to my way of thinking about how to improve indoor air quality and correct performance in air handling units by combating air leakage. And as you can see here, this is the objectives that were set out by the guide. So good practice to limit internal air leakages, outlines important measures to be considered in designing the unit to minimise leakage, and the recommendation all presents guidelines on how to correct the declared performance due to the leakages. So it talks about EN standards. The subject of internal leakages is specifically addressed within a few EN standards, and I'll come back to what they are shortly. Specifically, leakages in and around the heat recovery sections is raised in EN 16798-3, which Peter referred to a bit earlier. And for the purposes of tonight, it defines what the exhaust air transfer ratio is. The exhaust air transfer ratio is the level of carryover of extract air to the supply air. In other words, the percentage of exhaust air that we recirculate back into the space. EN 13053 specifies requirements for the performance and testing of an air handling unit, and it imposes on us as a manufacturer a responsibility for avoiding leakages from the extract airstream. And we take that very seriously. However, the above standards are not harmonised in EU regulation, and compliance with them is therefore not mandatory. And there is no real objective testing method that might be applied by market surveillance authorities. So the subject of internal air leakages within air handling units is a little bit of a grey area, and there is absolutely no guarantee that some manufacturers' equipment isn't leaking internally, and there's no way of verifying that for certain manufacturers, I should stress. So further on in this particular document, it talks about exhaust air transfer ratio. At present, the established factors for characterising the internal leakages are EATR, and that's principally for rotors. And they're both defined in EN 16798-3, and they are under revision in EN 308, which is the test standard for heat recovery devices. The PR means it's provisional at the moment. It's been published for consultation, but it's not yet a published standard. And they've been adopted actually within Eurovent's certification criteria. So in other words, if an air handling unit manufacturer is Eurovent certified, they are in the not too distant future going to have to declare amongst other things, the exhaust air transfer ratio in their published technical information. And that gives clarity to the industry as to how much an air handling unit is actually leaking in reality. This particular document, it's very interesting. It's 38 pages long. It is available for download from the Eurovent website, and I would encourage everybody to have a look at that. It's rather too obviously dense and complicated to go through in detail during the course of this presentation. And there is ongoing work to revise EN 308, and I'll come to that in a moment. So what standards apply and what advice and verification is available for the subject of minimising leakage? So again, EN 308, the provisional version was published in May 2020, and it's the test procedures for establishing performance of air-to-air heat recovery devices. EN 1886, which is essentially the mechanical performance of an air handling unit box, again, that is being published as a provisional document, and the revised version will be published fairly shortly. We, of course, as an industry in the UK, have to comply with Part L. And EN 16798, which Peter referred to earlier, that's a fairly new document. And there is an accompanying document which actually teaches you how to interpret Part 3, which is, I think, fairly quaint. However, all of these standards are enshrined within the Eurovent certified performance system. So if you specify or purchase a Eurovent certified air handling unit, you know that the manufacturer is either in compliance with the existing standards or is working to enshrine the provisional standards within their standard test procedure and certification of their air handling unit. So EN 308, it has some key changes. They are, in addition to laboratory tests of the heat recovery components, which is all that we had to do up until now, it will include laboratory tests for the heat recovery component, that's HRC, fitted into the air handling unit. You might find that it's a bit surprising that that wasn't the case before, but that's the reality. The effect of mounting the heat recovery component in the air handling unit was never tested previously. Leakage testing has been refined. EATR and OACF are implemented and defined. So in other words, the testing that we have to do to establish the EATR in principle is defined now within the standard. And several terms and definitions have changed, e.g. categories of heat recovery components, and I'll come on to that in a moment. So all heat recovery components are now defined. What I've done is edited this slightly from the document. There is a few extra options in the EN 308, but effectively what we're talking about is, excuse me, recuperative heat recovery components. That's either cross-flow or counterflow plate heat exchangers with or without humidity transfer. HRC with intermediary heat transfer medium is essentially run-around coils or heat pipes. And anything that's in category HRC2 is probably, in all honesty, not a leakage issue that could affect indoor air quality. And then regenerative heat recovery components, that's essentially rotary wheels, whether they're non-hydroscopic or hydroscopic, and hydroscopic being they transfer humidity between the two air streams. So what the standard now does is it defines testing and validation for amongst other things, the leakage of these devices. So when it comes to cross and counterflow plate heat exchangers and indeed run-around coils and heat pipes, there cannot be more than 3% leakage internally through the heat recovery device. If there is, according to any testing that's gone on, a higher rate of leakage, then the EATR has to be declared for that particular configuration of unit. If, however, you are a Eurovent certified manufacturer of air handling units, you then have to test an air handling unit with a plate heat exchanger in it, and the acceptance criteria for leakage within a standard air handling unit with a cross or counterflow plate heat exchanger, according to Eurovent, is 0.5%, not the 3% that would mean that you adhere to the EN standard. So in other words, Eurovent is much more onerous on the air handling unit manufacturer to limit the leakage inside the air handling unit. And when it comes to rotors, the subject of rotors we covered actually in our presentation back in January in this group. It's a much more nuanced conversation. What I would say is that a thermal wheel unit with fans drawing through the rotor, fitted with a purge sector and with pressure balance controls, has an EATR less than 1% according to REVA, but in reality close to or equal to 0%. So in other words, correctly configured air handling units with rotors can leak less than a plate heat exchanger that has been Eurovent certified, and certainly less than a plate heat exchanger that has only been tested to EN 308. And if you want details of that previous presentation, they're actually on the HVAC Systems Group webpage, and there is a YouTube link as well here in this presentation. So what about the casing? Well, the casing, we're obliged for Part L compliance to comply with EN 1886, which defines the leakage standard for the air handling unit, and of course this will be revised shortly. We must achieve Class L2 leakage for air handling units. Eurovent independently tests manufacturers' units for leakage, and test results are available to view by going onto the Eurovent certification webpage. So any manufacturer that is Eurovent certified has had to submit their equipment for independent testing by Eurovent, and then Eurovent publish those criteria, those definitions on their website. So if you want to know precisely how much an air handling unit leaks by, you can go to Eurovent for independent verification. The vast majority of manufacturers in the UK are not Eurovent certified, and therefore there's no independent body that you can go to verify that the manufacturer's claimed leakages are correct. And then filters, just following on from what Peter was saying earlier on, contained within the provisional EN 1886 is a section on acceptable filter bypass leakage. I'm not going to go into the details here because we don't have time, but these are the acceptable figures. And again, if you are Eurovent certified, Eurovent publish essentially the filter bypass leakage that's achieved when the unit is tested. And in this case, as you can see here, despite the fact the unit was tested with an F7 in old money filter, the bypass leakage was actually a classification F9. So in other words, there was virtually no bypassing of the filter frame through the air handling unit because of the nature of the way that we construct our filter frames. So just a quick summary of all that. If I was a consultant, and I'm not, I would be looking to implement in my standard specification all the relevant information that limits the leakage within an air handling unit. And I would enshrine that in, like I say, in my standard specification. So this is, if you like, a checklist. If you are a consultant and you want to do that, you need to meet Part L leakage. L2 is the standard in Part L. Eurovent independently verifies the manufacturer's claim. You need to minimize the bypass leakage. I've just realized I've made a little bit of an error because I haven't filled in the standard, but it's EN 16798-3 and 1886. Eurovent tests and publishes the filter bypass leakage. The heat recovery efficiency needs to be in accordance with PRN 308. Again, Eurovent tests this, and a Eurovent certified unit leaks less than an EN 308 certified product. When it comes to rotors, put the fans in the correct position, fit the unit with a purge sector, and include pressure balancing. The manufacturer is in theory capable of doing all of those things. There is a lot more detail in the Eurovent document, and if you include all these options, the results in an EATR of less than 1%. Request the EATR figure from the supplier if you're concerned about the amount of leakage potentially in the air handling unit. A Eurovent certified manufacturer will soon be obligated to declare the EATR. So you will be in a position to ask the manufacturer to give you that information, and they should be able to do so in the not too distant future. And what I would encourage everybody to do is to enshrine the updated European standards into their standard specification and refer specifically to the requirements contained within them in respect of minimising leakage to improve the indoor air quality. So thank you for your attention. I will hang on to do questions after Graeme's completed his presentation.
Thanks for that. Can you hear me okay? So what I'm going to ask David is if any questions come through on the Q&A, please, David, could you respond to them, because we're a little bit short of time and we might not actually have any time at the end. And I just want to make sure people get their answers to their questions. So thank you very much for that. Great summary as well. So last but not least is Graeme Fox. He is Head of Technical at CIBSE. Graeme is a Chartered Engineer, a Fellow of the IOR and a Committee Member of our CIBSE HVAC Group. He has over 30 years experience in the HVAC sector, mainly in building services, air conditioning and refrigeration. And for the last 6 years, he's been working with the trade associations to help contractors with their legal compliance and technical needs. Over to you, Graeme.
Thanks, Mary-Anne. I will try and zip through this as quickly as possible. Running very short of time, I realise that. So, okay, the pandemic obviously highlighted the importance of ventilation, focused the need on good levels of ventilation inside buildings, non-domestic and domestic, but sadly also it demonstrated how inadequate many existing buildings ventilation systems are, in that they have little or no flexibility of output, as we've already heard the issues that entails. Really important because to look at retrofitting as well. The building standards are changing, we've heard that, we've already looked at that. Which is great for new build and major refurbishment projects, but of course 80% of the building stock currently in use will still be around in 50 years time, so upgrading the existing ventilation systems is really, really crucial. But as was mentioned earlier, how do we know when retrofitting is actually being effective? And I think one of the questions that was popped into the chat earlier on as well asked that question. Well, what we've been doing at the CIBSE Group is we've been looking at indoor air quality for a number of years now. Because we actually had an issue in our own office, our old office, so we've been looking at it very, very closely. Why is it an issue? Well, we've already heard, it's been touched on by Pawel in the first presentation, that poor air quality actually affects our oxygen levels, which in turn makes us tired, less able to concentrate, irritable, more prone to infection. So it's really essential that we address this issue in everywhere: offices, schools, factories, all public spaces, really, shopping malls, cinemas, restaurants, etc. And these are all buildings that are currently being looked at through the coronavirus prism, obviously. But one of the reasons that good ventilation is a good COVID mitigation measure is actually because good ventilation is a good IAQ, or health and well-being measure generally. So the CIBSE Group, we have a health and wellbeing in buildings group, and that group created this beginner's guide to indoor air quality back in March this year. And the purpose of that guide was to present the crucial facts in a non-technical language. We've heard a lot about PM and VOCs and TVOCs, and what we're finding is we're needing to actually open up the conversation to a wider group. And the problem is that the general public don't understand what this terminology means. So the beginner's guide to indoor air quality strips out the technical language and presents to the reader what constitutes particulate matter, volatile organic compounds, and what it means, where the particulate matter comes from, where the VOCs come from, particularly in the home. And we're looking at that very closely at the moment in terms of things like scented candles that people frequently use at winter time. These nice Christmas candles might actually be giving some pretty nasty chemicals into your house. The second steps, we did the beginner's guide in March. We then brought out the second step in that, which is a guide to good practice in indoor air quality, in August, and we're currently working on a solutions guide. So essentially, we have put out to consultation a draft of a solutions guide. So we've explained what the issues are. We've explained at what point the contaminants become problematic or dangerous to health, and now we're creating a guide which is actually going to point building managers and end users towards what they can do to actually mitigate when they've demonstrated there's a problem. It's estimated in the UK we spend around 90% of our time indoors. So to not look at the quality of the air that we're breathing in our buildings is frankly criminal. So the BESA Group, we've been working on COVID guidance, the same as CIBSE has pretty much since the start of the pandemic. February 2020, we brought our first guidance out. It's been evolving through time. We've taken on board guidance by CIBSE and REVA, among others. And we produce practical guidance. So the idea of this is practical measures for building services operators, essentially for our members to be able to address what the issues are when their clients are coming to them with concerns about COVID, last year in particular. We've looked very closely at the CDC reports. So the CDC report, this is from the Guangdong restaurant outbreak last year, right at the start of the pandemic, really. And what we found was, when you look at that first report, which was published in April 2nd last year, that was very, very basic. It was quite unscientific. And the weak conclusions, unfortunately, were latched onto by the mainstream press, saying silly things like air conditioning spreads coronavirus. The sketch of that restaurant itself was very misleading. You can see here, it's the suggestion is that there's a small restaurant with 5 tables in it, or 6 tables in it, which turned out to be utter nonsense. What was of note in that report, that initial CDC report, they took 6 swab samples from the air conditioning unit that you can see in the top right of the image, 3 from the air inlet and 3 from the air outlet of the AC unit, and all of them actually proved negative for the COVID-19 virus. But the report still somehow managed to conclude that air conditioning spread the coronavirus, according to our mainstream media. When you look at the sketch plan here in the second report, which was published a couple of weeks after that first one, you can see that actually that very basic sketch was nonsense in terms of the restaurant layout. And what this did, when we saw the full floor plan for that restaurant, it actually showed that it was a catalogue of errors in that restaurant that led to a stagnation of air in a particular zone, and a revelation that the extract fans weren't even working. So on the left hand side you can see 4 extract fans, 2 at the top and 2 at the bottom, and it transpired they weren't even actually operational at the time. The only air that was coming in, the only makeup air that was coming into that building was through the lift shaft. So every time somebody came up or down in the lift, at the bottom right corner there was a bit of air infiltration through the lift, and there was an extract only by the 100mm exhaust fan in the toilets at the bottom of the screen. It turned out that the occupation density in the restaurant was 1.55 square meters per patron, which is laughably low. It was Chinese New Year's Eve, and it packed extra tables in to try and maximize profits, but it actually meant, with that lack of air supply, that the air supply was only 1 litre per second per person as well in the restaurant, which is quite worrying. But I'm going to skip over this to try and get to where what we've actually been doing about it. And if anyone wants me to go back on some of this stuff afterwards, I'm quite happy to do it separately and take it up. I do want to just focus on the website www.40to60rh.com. Really important to consider humidity levels. We talk about contaminants in the air. We often don't think about the humidity. That website actually explains really well the golden band between 40 and 60% RH, and it's not in terms of how the virus is affected by humidity or temperature. It's actually about how the human body reacts. So that kind of golden band between 40 and 60%, the human body's ability to fend off viral attack through the respiratory tract is hugely improved. And this is why in winter time, when the RH obviously drops, 20-25%, the rate of infection of viruses such as common colds and flu is incrementally increased, which is why we have large numbers of hospitalizations and death every year. So that's really important just to highlight that. So what have we been doing at the BESA Group? This is a snapshot here of readings in our London office. So we installed Airthings IAQ monitors in our offices in London and Penrith to ensure our own staff were safe by maintaining good ventilation levels and keeping the crucial CO2 level down, really crucially. We did see in London that the CO2 level was actually quite low throughout the day, which was very good. And last week we actually had a technical committee meeting, and we had more members turn up for the face-to-face meeting than we expected. But I was able to actually monitor in real time that the CO2 level in the meeting room didn't rise to alarming levels, which was very, very useful. I've got a note here about other options about air handling units using HEPA filtration and UVC and things like that for air cleaning, but we'll come on to that afterwards. I did want to point out a little bit of unforeseen consequences. So the Penrith office we actually thought wouldn't really be too much of an issue in terms of CO2 levels. It's a relatively rural office. You can generally open windows, although on one side of the building, the top of the image, as you can see, is actually the A6, which is the old Shap Road. So there's a lot of tractors and lorries and things sitting idle in their engines out there. What we've done is we've installed local air cleaners around the building, because the building itself doesn't lend itself to permanent mechanical ventilation. So we've installed local air cleaners around the building, and what we've been able to do is prove that they are actually working well in keeping the particulate matter down and keeping the contaminants down for our staff. What we did find was we had a massive issue with radon in the office. So Pawel mentioned earlier on about radon levels. The ionizing regulations state that annual average levels above 300 becquerels per cubic metre require employers to take action to restrict exposure to employees, and we actually had some reasons in excess of 2,000 at some point, so we've had to take on some remedial work. The radon levels anywhere where there's volcanic rock essentially in the UK, we have big radon issues, so the dark areas that you can see on the map there. What it has allowed us to do, of course, in the office is demonstrate the importance of good ventilation. So as I say, with having the technical committee meeting last week and being able to monitor the CO2 levels and the various readings through the day as the meeting was going on, we could see that the good ventilation in our London office is actually working really well. And it's also been able to prove that the local air cleaners that we've installed in the office in Penrith are actually working very well as well. I think that just to summarise, really, to finalise, we've proved that good ventilation or effective ventilation is really good at solving some of the indoor air quality issues. However, energy efficiency is obviously a topic that looms very large over every business now, and really the big question is, what is the trade-off between the indoor air quality and the energy consumption in terms of net zero specifically, and how do we as engineers articulate that message? So I've cut that really short. And as I say, if anyone wants any more on that presentation, I'd be happy to follow up on it separately.
Thank you so much, Graeme. That's really interesting, the work that you're doing there. So hopefully the audience found that interesting too. So we do have actually a little bit of time for questions. So I am going to just go down the list. I know some of them are being answered on the way. But if I can call them out, or maybe some of the ones that haven't been replied to. So we've got one here, and I don't really mind who responds. I think this one was directed at Peter initially, but the question is, have we become a little fixated on HEPA filters in relation to COVID, when most building ventilation systems cannot accommodate them without expensive modifications? Meaning multiple small free-standing air purifiers are often considered, when in fact some ventilation systems could be made COVID-19 capturing with coatings on standard filters. Peter. Yes,
very good question. Good if we had half an hour to go through all the points involved, I think, but yeah, I mean, so far the solutions that have come up have involved use of HEPA filters in small freestanding units, essentially to, I would suggest, be good at mopping up in areas close to the source of particles. If you're talking about COVID-19, close to people in their beds in the wards, this sort of thing, and they've proven to be, quite effective, certainly in that study we looked at over time, providing they have a good way of dealing with the airspace. They need to be well positioned and have the capability to handle the air volume into which they're placed. There is, in my view, a largely unexamined potential for existing systems to be fitted with low energy air filters of high efficiency, i.e. the EPM1 to high efficiency in existing systems, making use of recirculation. This is something that needs to be carefully applied. And so, you know, you need, as David Black was mentioning, to have well sealed filters, also well positioned in the system, so that you're making use of all the filters on recirculation and on supply side to get the maximum total efficiency out of the system. And these are, you know, going to be suitable maybe for legacy air handling unit systems, and there are hundreds of thousands of old ventilation systems around the country. So it is a case-by-case situation. So there's going to be no quick, you know, magic bullet for this. But if you make use of the standalone where possible, if that's what you've got, check with air monitoring it's delivering the results needed. And obviously upgrade the existing system where you got it.
And David has got his hand raised.
Yeah, I just one thing to add, and it's actually quite pertinent to where Graeme comes from or came from yesterday. We were called in by a company in Dundee, actually to replace all the filters in their air handling units with HEPA filters. Some of the air handling units were cross-plate heat exchangers, so there wasn't particularly any leakage within the air handling unit. And the net effect of upgrading to HEPA filters was actually to reduce the amount of supply and extract airflow by in excess of 10%. So ultimately, it was self-defeating. You know, extra filtration was capturing potentially some stuff in the exhaust airstream, although extremely unlikely that there was much to it, and at the expense of reducing the airflow, which ultimately was to the detriment of the indoor air quality, and in all probability did nothing to prevent any spread of COVID within that particular building.
It sounds like we really need to look at whether the HEPA filter is the right solution. And Peter, obviously you've picked up some maybe solutions that don't require going to that much detail, and maybe we don't even need that much filtering, is what we're saying.
I think filter optimization has to be it. Low energy filters that have low operating pressure drops aren't going to consume a lot of fan energy, but will deliver high filtration efficiency. And if you can multi-stage those filters, there's tremendous potential there to get much cleaner air at low cost, low energy use. And unfortunately, a lot of the existing systems don't really put much of a focus on this area of improvement.
Thank you. And so we've only got a couple of minutes left. So Graeme, I'm just going to perhaps ask you a question. So all this information that you've gathered, where are you going to go next with it? Are you going to use it for anything, or are there any other buildings that you think would be worth monitoring?
Well, one of the reasons why we started going down this road of the IAQ stuff is actually to try and promote the idea of buildings as safe havens. It was primarily driven originally by, I mean, Peter, you mentioned earlier about Rosamond could see Deborah's the issue that she had with her daughter, and it was about outdoor pollution and drawing the outdoor air into buildings, which clearly, if you're just opening windows up and you have a lot of outdoor pollution, then actually you're exacerbating the problem. You're not making the building safe, and that's really where we're going with it all. The idea, once we get our third part of our suite of documents ready, is to actually be able to present that and try and deliver this idea of buildings as safe havens. Initially, I was thinking about some kind of certification scheme for, you know, for buildings being able to demonstrate in live time with their own monitoring kit. You know, a QR code as you're going into a restaurant, for example, showing the indoor air quality is good. Once people are aware of what good indoor air quality is, it would actually help businesses to alleviate fears that a lot of people still have about going into public buildings.
Yeah, no, I think you're right, Graeme. And so we are at the end of our time. So I would like to say thank you to all our speakers, to Graeme, Peter, David, and also Pawel, who obviously isn't with us now. I think Safe Haven is a lovely ending for this. And I would wish you all a safe haven and a very Merry Christmas. And hopefully we will see you at the next meeting, which is on the 16th of February. And we will see you then. Thank you so much for joining us. See you next
Thanks,
time.
Marianne.
Bye.
Sure.
Bye.